Hi, today we're going to talk about naming ionic compounds. So as we mentioned in the last video, ionic compounds are formed when you combine a cation with an anion, and these are held together by the electrostatic force because they have opposite charges. So ionic compounds are unique from other sorts of compounds, the covalent compounds we'll be talking about next, in several different ways. First, they have very high melting points. So you may or may not have ever tried melting sugar. You have to be really careful doing it so you don't burn sugar, but you can melt sugar. It's pretty easy to do on the stovetop. But have you ever tried melting table salt? I mean, you can put that stuff in your pot on the stove and crank it up all the way and it won't melt. In fact, you can put it in your oven on self-cleaning mode and it still won't melt. So ionic compounds tend to have extremely high melting points. Sodium chloride, for example, is somewhere around, I believe, 900 Celsius. The other thing about ionic compounds is they aren't flexible, and if you try and bend them, they actually shatter. So as a comparison between two types of compounds, if you take a hammer and you hit, let's say, a table, you're going to make a dent in the table. So the wood that the table is made of actually deforms. It bends out of the way. But if you try and take a very large lump of halite, which is sodium chloride in crystal form, and you hit it, it's just going to shatter into little pieces. Many ionic compounds dissolve easily in water. There are some that don't, and we're going to talk about those when we start talking about chemical reactions. But we encounter a lot of ionic compounds on an everyday basis. You're going to see a lot of them in chemistry lab, and so it's important to talk about how we name ionic compounds. So first of all, we're going to start with a generic introduction to chemical nomenclature, where basically you show what is in a compound by giving the element symbols, and for each element, there may be a subscript that tells how many atoms there are of that element. Now, if there is no subscript, that means there's only one of each element. With that in mind, let's take a look at some principles that govern the formation of ionic compounds, and then we'll talk about naming them. So the reason that anions and cations come together is because they have opposite charges, and nature is trying to avoid a buildup of charge. And because the idea of them coming together is to neutralize charges, the charges on ionic compounds will add to zero. If you think about two particular ions, and in this case I have calcium and oxygen coming together, how would these combine? So let's look at the net charge. We've got a +2 charge on the calcium and a -2 charge on the oxygen. And so if we add these together, +2 - 2 equals 0. That's the point. You want to make calcium oxide. You're going to get 1 calcium for every oxygen. That will give you a net charge of 0. But now let's look at some different ions. Here we have ions made from magnesium and bromine. And let's think about if we put these two together, what the net charge would be. As we talked about in the last video, if you look at where magnesium is on the periodic table, you'll see it should have a charge of +2. And bromine, which is a halogen, should have a charge of -1. If you put these two ions together, you have +2 - 1, add those up, and you get a net charge of +1. Now this is not 0. Well, what does that mean? It means we still have charge left and something is going to need to neutralize it. What would you need to neutralize this positive charge? You'd need something that was negative. So we could, for example, throw in another bromine. And what would happen if we did that? Okay, add another -1 charge, and now our net charge is 0. So for every magnesium you have, you're going to end up having 2 bromines. And we would write that as MgBr2. All right, one more. Let's use oxygen again, but let's combine it with potassium this time. So again, let's do our net charge. We have a +1 charge on the potassium and a -2 charge on the oxygen. +1 - 2 gives us a total of -1, which is also not 0. And so we need to do something to bring that negative charge up to 0, and what we can do is we can add another positively charged thing. So let's add another potassium, and that would add another +1 to our net charge calculation, and that would give us a net charge of 0. So we're going to write that as K2O. Now, one thing you'll notice as we write these is that we're always putting the cation first and the anion second, and there's a reason for that. Because when we're naming ionic compounds, we start with the name of the cation, and then we do our anion. There are a couple of possibilities for the anion. You could have a single element ion, in which case we change the element name so it ends in "ide." And if it's a multiple element cation, which we're going to talk about in more detail later, we're just going to use the name of the anion. So let's do some examples. NaCl is table salt, and I'm starting with this one because we've talked about table salt and I've used its chemical name before. So start with the name of the cation. The cation is Na+, that's sodium, and then the anion is a single element. It's chlorine, but we're going to change it so it is now chloride. So it ends in "ide." That's going to be sodium chloride. Okay, here's a different one. SrF2. Start with the name of the cation. Sr, if you're not sure, you can always look at your periodic table. Sr is strontium. And then F2, well, we've got fluorines there. We want to change the end of it to end in "ide, so it's going to be fluoride. So this is strontium fluoride. So the two that we've just done are fairly straightforward, and if all ionic compounds were like that, this would be a piece of cake and we wouldn't have to spend any more time on it. But unfortunately, ionic compounds are not always this simple. And one of the ways in which they can be complicated is that if you're talking about elements in the D block and the F block, in their elemental state, these are cations, but those cations can have different charges. We talked about this briefly when we were doing electron configurations of ions. So now we need to think about what happens when you have cations with different charges. And let's use iron for an example. Generally speaking, in nature, you commonly find iron with two different charges, iron 2+ and iron 3+. So now let's think about what would happen if we combined each of these with oxygen. Remember that oxygen has a -2 charge. For iron 2+, it's pretty easy to see that you just need one oxygen to balance the charge and get a net charge of 0. With iron 3+, now that's where the math gets a bit tricky, and I'm just going to say that it ends up being Fe2O3, so you get a total of +6 charges from the irons and -6 from the oxygens. So if you think about what we said before and using the rules we followed before, this would be iron oxide. This is also iron oxide, but they're two completely different compounds. So we need some way to distinguish between these two sorts of iron oxides. And so what we're going to do is we're going to indicate the charge on the transition metal, which in this case is iron, and we're going to do that by writing it as a Roman numeral in parentheses. So the top iron oxide would be iron 2 oxide, which tells us that iron has a +2 charge. The bottom iron oxide would be iron 3 oxide. Based on this, what would the chemical formula be for cobalt 2 chloride? Let's think about this. Cobalt 2 is going to have a +2 charge. Chloride comes from chlorine, and that's going to have a -1 charge based on its location in the periodic table. That tells us that we have to have 2 chlorides for every cobalt. The formula for this would be CoCl2. Now notice in the formula, it does not tell us what the charge on the cobalt is because we can figure it out knowing that it's a neutral compound. Let me explain why. Okay, so let's look at CrO3. This is another oxide. Okay, so we know that oxygen has a -2 charge. There are 3 oxygens, so we're going to have -2 times 3, so that's going to be -6 from our oxygens. So to have this chromium oxide have a net charge of 0, we're going to have some charge on chromium, which when you subtract 6, remember the -6 comes from the oxygens, is going to equal 0. So what charge would make this work? +6. That tells us that the charge on chromium here has to be +6. We can deduce that without notation because we know what the charge on oxygen is. So this is going to be chromium 6 oxide. One of the things that I mentioned is if you have an ion that's made up of more than one thing, then you just use the name of that ion. That's true whether you're talking about cations or anions, although there are a lot more polyatomic anions than cations. So these ions are made up of atoms that are bonded together covalently. We haven't really talked about covalent bonding yet. That's coming up next. But just know that these stick together and they act as if they were one unit for purposes of being an ion. So this particular ion right here is called bicarbonate. That is the anion in sodium bicarbonate, which is what we use as baking soda. It also happens to be a great way to neutralize acid. So we need to add Na+. So if we put these together, we have to double check the charge. Bicarbonate has a -1 charge, sodium has a +1 charge. So we're going to have NaHCO3. And again, sodium goes first because it is the cation. Bicarbonate comes next. Now, when you're dealing with polyatomic ions, sometimes you need to have more than one of them. And the way to make that clear is to put the entire ion in parentheses and then add your subscript. So for example, let's say we're talking about bicarbonate again, but instead of talking about sodium bicarbonate, we're talking about calcium bicarbonate. Now calcium, of course, has a +2 charge. And in order to get a net neutral charge, a charge of 0 for this ion, we're going to need 2 bicarbonates. So we're going to write it this way. And if you look at the way this ion is written, we have HCO3 in parentheses, and then we have a subscript of 2 outside of that to indicate that we have 2 bicarbonates. And imagine what this would look like if we didn't put the parentheses in. We would try and put a subscript of 2 after the bicarbonate, and it would end up looking like HCO32, which is obviously not what we mean. So that's why we use parentheses. The last thing I need to talk about is hydrates. You're also going to be using at least one hydrate in your lab. So basically, ionic compounds often have water molecules incorporated in their crystal structure. So basically, water molecules stick to ionic compounds even when they're solid. So a lot of times there is a set number of water molecules that will stick to each unit of ionic compound. And so what we're going to do is we're going to write that in the formula. Calcium chloride often comes as what we call a dihydrate. So here's calcium chloride with waters bound to it. Calcium chloride, of course, is our ionic compound. Then there's that dot that separates the ionic compound from the number of waters that are bound to it. Now, when we're naming hydrates, we're going to first pick out the ionic compound and name that the way we always do. And then we're going to look at what's after the dot, pick the appropriate prefix for the number of waters, and write that along with the word hydrate. So here are our prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Now, I personally have never seen anything above a heptahydrate, but I know it is possible to have more. So back to the ionic compound we were looking at before, CaCl2, that's calcium chloride. Then we have our dot, 2H2O. We have to pick the appropriate prefix. We have 2, that's going to be di. So that's calcium chloride dihydrate. So you can also go from this written name to a formula, right? If I asked you for rubidium chloride trihydrate, we just dissect the name. Rubidium has a +1 charge. Chloride, that comes from chlorine. We know that has a -1 charge. Both of these, I got these charges based on their location in the periodic table. So that's going to give us RbCl. And then we have the hydrate. We know that's going to give us the H2O. And then we're going to look at the prefix, right? Here's the prefix table. So we've got tri, which is 3. And so we're going to write RbCl dot 3H2O. I've been throwing a lot of rules at you, but once you master them, you're going to easily be able to translate names of ionic compounds into chemical formulas and translate chemical formulas into the systematic name that we use in chemistry. I hope this was helpful, and I look forward to seeing you again soon.